All right, welcome to the third installment of the Theology of Everyday Things. So this is a course in practical theology. So normally when we talk about theology, we oftentimes think about spiritual or moral issues, but um, we're in this series we're talking about practical effects of theological considerations. So in this lesson, we're talking about how to build an artificial intelligence using the doctrine of man. And so, as you might have noticed from the previous parts of this is not metaphorical. Um, this is not an analogy. This is using the doctrine of man as part of building an artificial intelligence. So, kind of a review. So remember, theology is not just about God. It's about all the things that stem from a God-centered worldview. Christian theology is about true things, not just preferences. And truth has practical value in the real world. And my goal in this giving these sketches is to help us open our minds to using theology even in the mundane aspects of our lives. That theology is applicable in a lot more places than you might expect. All right, so my goal here is to give these sketches to inspire you to broaden your perspective on how theology can be applied to life. So today we're talking about the doctrine of man. So let's talk a little bit about this doctrine. So, Doctrine of Man holds that humans are made in the image of God. Right? In the image of God, uh, God created them. Okay, so God breathed His life into us. All right, He said when He breathed His life, that's when man became a living being. Humans are caretakers of God's creation. That's what the dominion mandate is about. That we're in charge of it. Um, then humans are not just physical but also spiritual. And there's lots of references you could pull, um, but Jesus says things such as, don't just fear man who can kill the body, but fear God who can destroy both the body and the soul in hell. There's love the Lord your God with all your heart, soul, mind, and spirit. Um, so there's lots of different aspects where the Bible refers to humans as not just being physical entities, but also spiritual entities. Humans are also relational. It was not good for man to be alone. So that's why you have a husband and wife, because it's not good. The aloneness is not good. So this is kind of an overview of the doctrine of man. And just to in case it's not clear, the doctrine of man doesn't mean man as in male, but man as in human. So when we talk about the doctrine of man, that's the historical term for it. It is not male centric. It is simply using the historic term for human. So to start off with, we need to talk a little bit about the nature of reality, because this is one common contention um, in modern uh, discourses. So the nature of reality, there's kind of two perspectives, and the two perspectives is, first one is reality is purely physical, that there's no other reality besides what we can that besides what is in the physical environment. That there's or if there is, it doesn't interact with us. Okay, so reality is purely physical. Maybe God made something, but God is not touching things. Maybe there are angels, but angels aren't doing any things. But you, as a human, you are purely physical. Um, there's nothing else in our experience except the physical. The other point of view is that reality is physical and spiritual. All right, and the thing that we always have to remember in all of this is that reality includes you. Okay, so you can't take yourself out of the equation. We can't say, what about reality except for me? Well, we're talking about reality as a whole. So that includes people. So the question is are you only physical, or are you physical and spiritual? So if you believe that you have a soul, then you actually have to take the second option. Okay, so a lot of people, when we're talking about the nature of reality, the nature of exploring the world, we forget that 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 we are spiritual beings, and we get this idea that spiritual things are kind of these rare esoteric incidences, but actually spirituality is kind of at our core, and we'll get into that as we go along. But I want to point out that many people believe that physics is all there is. All right, so here's a quote from Steven Weinberg. It says, "I think that more and more the picture of nature, the outside world, has been one of an impersonal world governed by mathematical laws that are not particularly concerned with human beings, in which humans appear as a chance phenomenon, not the goal towards which the universe is directed." Okay, so it's an impersonal mathematical world. That's it. No spirit, no soul, just the outworkings of an equation. Richard Lewontin puts it like this: in order to properly understand the universe, people should reject irrational and supernatural explanations of the world and accept a social and intellectual apparatus, science, as the only begetter of truth. Now note, he's not saying that science should be a begetter of truth. He says that science should be the only begetter of truth. That supernatural explanations uh, they basically lie in the same place as irrational explanations. So again, he's saying that physics is all there is, and we should only explore things as if they are physical. Um, Many go further and state not only that physics is all there is, but that physics can only contain computation-like operations. This is known as the physical church-Turing thesis, and actually, this is actually a natural corollary of physics, because once you start asking, well, what is physics? What is natural? Um, then once you have to define that, really the only workable definition that comes out uh, is computation, something that is in some sense computable. Um, and so that might be surprising, and not everybody agrees with that, but the people who don't agree with that tend to not be able to define uh, physical and non-physical well. They don't have a definition. They just assume you should know what it is. Anyway, so the only definitions uh, that really are workable for separating out uh, physical from non-physical comes along by computation. So if humans are only physical, so if we only have a body but no soul, and physics implies being computable, then that means a true artificial human intelligence could be built, because that's basically what the way those relate. If we're only physical and being physical implies being computable, well then if we have enough computation available, we can make a human. Maybe we don't have enough now, maybe we need bigger machines or more connections or something like that, but ultimately there's no impossibility about making an artificial intelligence. We shouldn't be surprised at it. We should maybe even look for it as a goal. That's if humans are only physical. But let's say if humans are spiritual, if we have a body and a soul, and the limits of physics are equivalent with the limits of computation, then we should expect that there are things that humans can do that computers cannot. And if that's the case, then artificial human intelligence is not possible. We cannot create a computer that will do all the things that humans can do. So I want to give you kind of an intuitive description of the difference between humans and computers. And this is from the book 0 to 1 by Peter Thiel. It's actually a really great book. I highly recommend it. It's basically the application of intelligent design and the doctrine of man to business. He doesn't always use those terms, but he uses terms very much like that. Here's what he has to say. Computers are far more different from people than any two people are different from each other. Men and machines are good at fundamentally different things. People have intentionality. We form plans and make decisions in complicated situations. We're less good at making sense of enormous amounts of data. Computers are exactly the opposite. They excel at efficient data processing, but they struggle to make basic judgments that would be simple for any human. In 2012, one of Google's supercomputers made headlines when, after scanning 10 million thumbnails of YouTube videos, it learned to identify a cat with 75% accuracy. That sounds impressive until you remember that the average 4-year-old can do it flawlessly. When a cheap laptop beats the smartest mathematicians at some tasks, but even a supercomputer with 16,000 CPUs can't beat a child at others, you can tell that humans and computers are not just more or less powerful than each other, they are categorically different. So what's interesting about all this is that we actually know about the fundamental limitations of computers. This is actually a well-studied field. And so most people are actually surprised to learn what it is that computers can do. Okay, because computers really only can do two things. They can do simple computation, add, subtract, multiply, divide, and conditional branching. And what conditional branching means, it says if this is less than this, then do this set of instructions, else do this set of instructions. That's pretty much, they can do that. And then they can do input and output. They can talk to our screens and keyboards and hard drives and that sort of thing. So there's also storing data, but storing data is actually just another aspect of input and output. So all of your RAM on your computer, your hard drive, your USB sticks, all those, that's storing data, but that's actually just input-output. It inputs and outputs to those devices. So that's it. That's all that they can do. So you might say, well, if that's all computers can do, if they can just do these simple computations, what makes them so advanced? Well, what makes computers advanced is simply that they can do these things really, really fast. Okay. So, for example, a typical computer can do a billion, that's a billion with a B, operations in 1 second. Okay, so that's what makes them seem advanced, is that they're able, they're only able to do these very basic mathematical operations, but they're able to do a whole lot of them. So when you move your cursor across the screen, for instance, what that's doing is it's moving this pixel data on and off of your screen, and if there's some translucence, it'll be adding pixels together, and it's just doing it really, really fast. And so if you can do computation, if you can do a billion computations in a second, you can do some pretty cool looking things, and make it work smoothly and seamlessly, and it looks almost like magic. So the other thing they can do is they can store a lot of data. Um, so these two things together are what cause people to think about computers as being these very advanced machines. But really, they're really just simple machines following simple instructions. They can just do it really, really fast. And if you've ever seen the movie Short Circuit, it's one of my favorite movies. They have this great quote about computers. I hope the sound works on this. We'll see.
It's a machine, Scroder. It doesn't get pissed off. It doesn't get happy. It doesn't get sad. It doesn't laugh at your jokes.
It just runs programs.
It's a machine. It doesn't get scared. It doesn't get happy. It doesn't get sad. It just runs programs.
Yeah, so that's what computers do. They just run programs. They now in the movie, obviously, the machine did more than that. The machine became alive and had consciousness and whatnot. But that's because Short Circuit is a fantasy movie, and it's a great fantasy. Fantasizing about computers coming to life is just as interesting as fantasizing about elves in the woods or gnomes that come and fold your laundry or anything like that. But ultimately, what computers actually can do is they just run programs. So if once you understand that computers just run programs, understanding the limits of computation is important. Now, first, I want to talk about some obvious limitations, because now I'm not going to spend a lot of time on these, but it's always good to note. All right, first of all, computation doesn't have any consciousness, and one thing that I think is interesting is that we forget that our primary data in the world comes from our experiences, right? The ultimate of empirical thinking is your experience, but experience itself is mediated through consciousness, right? And consciousness is not anything in physics, right? It actually is itself spiritual. And so one thing that I think is interesting is that like a lot of people again think that spirituality is something that's out there or rarely happens, or something that's weird or not a normal part of life. But actually, your consciousness is the primary data point that you have about the world, and so it is, and your consciousness is a spiritual operation. And so actually, the thing that you have the most data on, the most data for, the most common experience that you have is actually spiritual. So the second thing is no purposes. Computers don't have purposes. They just run programs. They're not intending anything. They're just doing things, right? Has no desire. It doesn't want anything. A computer is just as happy if I smash it with a hammer as if I let it run forever. It doesn't have any desire. So these are the things. There's actually a great book called Purpose and Desire about what makes living things living, and it's basically saying that we've been trying to pigeonhole living things into this physicalist uh, idea for a long time, but what we really need to do in biology is take purpose and desire seriously. So anyway, so those are obvious limitations of computation, and we're not really concentrating on those. I just wanted you to take some time and think about the fact that your primary experience of the world is actually spiritual and not physical. But there's less obvious limitations of computers. The main thing being that computers cannot themselves analyze code in any deep way. And this is formalized in kind of two famous theorems in computer science, known as the halting problem, and then an extension to that called Rice's theorem, which basically says you really can't analyze any large-scale, any non-trivial property of a computer program with another computer program. So kind of as an explanation of what these things are saying is that a computer can perform cyclical instructions, but they can't predict the results. So a cyclical instruction is where you repeat something over and over again. And they can perform these sorts of instructions, but they can't predict the outcomes. Okay. And so another way to formalize this is to say that computers can't generate new axioms. They can only generate new theorems. And that's the result of some mathematics from the 1930s, actually, known as Gödel incompleteness. So what are axioms and theorems? Okay, well, to talk about this, we need to kind of go back to geometry class. So an axiom is a self-evident statement assumed to be true, but which cannot be proven. Okay, so these are things like between any 2 points is a straight line. That's an axiom of geometry, but you can't prove it. So that's what an axiom. An axiom is a statement. Its evidence is itself. It can't be proven. So here's our example. Given 2 points, there's a straight line that connects them. Another good one is things that are equal to the same thing are also equal to each other. So if A is equal to 3 and B is equal to 3, then A is equal to B, right? So that's an axiom. So a theorem is a chain of axioms that leads to a result. So you basically take a bunch of axioms and you say, okay, well, if this axiom is true and this axiom is true, what else does that tell us, right? And so an example of a theorem is the isosceles symmetry theorem that says two sides of a triangle are equal if and only if the angles opposite them are equal. And you could prove this by combining different axioms together. So the thing about computers is that computers can generate theorems, but not axioms. You actually need humans to generate the axioms. And you might say, okay, well, fine, you need humans to generate the axioms. Well, let's just generate the axioms we'll need and then set the computer off and running. The problem with that is that there's actually an infinite number of them. That's one of the things that Gödel incompleteness tells us, is that there's an infinite number of them that you need. So you can't just encode all of them into a finite computer, because computers only have a finite amount of memory. You can only have a finite length computer program, and so we cannot encode an infinite number of axioms on them. So, so if you recognize that computers need axioms to generate theorems, and computers can't be the source of axioms because there's nothing that's self-evident to a computer because there's no self there, right? And so they need humans to generate these axioms for them. And so this is really how machine learning actually works, is that you start a machine learning process with axioms, and then you feed it data, and it infers results from that data, but it only works if the axioms that it starts with is relevant to the data it's being fed. Okay, if the axioms aren't related to the data, then it doesn't work. And in fact, much of machine learning works by massaging the data so it better matches the assumptions and axioms of the machine learning system. Now, everybody, we've all seen these headlines that say machine learning grows this or learns to do this or, advances in this way. And so they think that the machine learning systems itself is growing these abilities to do new things all the time. But that's not actually how machine learning grows. Okay, so kind of the actual process that happens is the machine learning system is created. The machine learning generates theorems for whatever system it's trying to solve. And this works for a while, but eventually we bump into a limitation of our machine learning system. And so what we have to do at that point is we have to go and we have to think about, well, what is causing this limitation? And so what'll happen is that the humans will then go and discover and add a new axiom to the system. And so now that we have a new axiom, the machine learning can now process more theorems based on these new axioms. So if you think about theorems are combinations of axioms, and so the machine learning can generate thousands of theorems from just a handful of axioms. But eventually it gets to a point where, it's not really generating, the theorems aren't matching what it has. It's not able to generate interesting new ones. And so what happens eventually is that we have to add a new axiom. These axioms may be small, it may be large, but once you add the axiom, then there's a whole new set of data that the machine learning is able to process. And so this process repeats on and on and on again. So what's the role of humans? So with humans, when you know that this human-machine split works, once you recognize that machine learning needs axioms, and that humans provide the axioms and machines generate the theorems, this helps you recognize when axioms are needed, and knows that it's you that needs to generate the new axioms. The computer can't do it for you. And then once you recognize that the system can only use the axioms it already has, it helps you recognize that you need to align the input to match the axioms being utilized by the system. So the thing is that most people in machine learning don't make these careful distinctions, and so they actually waste a lot of time not recognizing when this process needs to occur. But if you're familiar with this distinction between the human and the machine, and you know how it breaks down, that it breaks down along this axiom theorem demarcation, it helps you to see better when you're bumping into, when is it that we just need more computing power, and when is it that we actually need new axioms to move forward. And then you also know if you need new axioms, then you need to go to humans for that because your computers are of no help. So that brings us to our next subject, which is artificial intelligence. And no, that's not a typo. It really is artificial intelligence. So to begin with, I'm going to tell you a story. It's a true story. It's the story of the mechanical Turk. And so this was in the 1600s. There was a machine that they built that would play chess with you. All right, so it would actually beat most people in chess. You might be thinking 1600s, that's pretty early to have a machine that could play and beat chess. But indeed, they took this around to different fairs, and the machine would play different people in chess, and the machine would move the pieces, and it was able to successfully beat most people. So you might be wondering, well, how exactly did they do that? Well, the way they did it is pretty simple. So you've got this giant box of gears and a guy being operated by the machine, but in addition to that, you also had a guy in a box, right? So in addition to these mechanical gears, there's also a dude inside who was managing the gears. All right, and so this is how. So it looked like on the outside that you were playing against a machine, but what you were actually doing is playing against the man in the box. And he was basically just a very short chess player that could fit in the box and manipulate the machine. So it looked like you were getting the outputs of a machine, but you're really playing up against a human. And so this is actually the way that a lot of artificial intelligence companies actually operate. To some extent, they are all just dudes in a box. There's actually a book called Ghost Work that kind of gives you some insight onto this. The actual point of ghost work is to talk about workers' rights in this sort of area, but it does a good job of having also having kind of descriptions of what this work looks like, how it operates, and that sort of thing. So some examples of this is there was once a business called Card Munch, and it was a credit card, or not a credit card, a business card scanning application. And what it would do is it would basically, you could scan any business card and it would turn it into a contact on your phone. Now you've seen crazy business cards before, and you might wonder how could it scan any arbitrary business card, no matter how crazy it was, and figure out how to put that into contacts. Well, the answer is when you scan the card, the computer didn't try to figure out how to put that into your contacts. It sent it to some call center somewhere and displayed it for a person, and the person interpreted the card, typed in the data, and sent it back to you. All right. So it was pretending to be a program that did it, but it was really just a program that relayed it to a typist who then typed it out and sent it back to you. All right. So this was all, the use of the humans was completely invisible to you. They're basically acting as dudes in a box. There's once a program called Soylent. It's a Microsoft Word program, and basically it would rewrite paragraphs for you. So basically you could highlight a paragraph, right click and say, shorten my paragraph, right? And so what that would do is that would actually send your paragraph off to 5 different people, and they would all try to attempt to write a shorter version of your paragraph. It would then send those paragraphs off to 2 or 3 different judges who would then pick what the best rewrite was, and then that rewrite would then be inserted into your system. So to you, it looked like the machine was doing it. You right click, you say shorten my paragraph, you wait a couple minutes, and blammo, your paragraph was shortened. But really what was happening was that it was going out to some guy in a call center somewhere who's doing it, who was a human doing it. So Expensify is a receipt scanning system that works quite similar to Card Munch. It would take your receipt, scan it, and send it off to someone else to type in the details. Now, what happens in a lot of these is that there's kind of a feedback loop that happens. So if you scan enough receipts that look the same, then eventually a programmer will say, okay, well, I can now write a program that will identify this particular look of a receipt and know how to process it. And then when it gets receipts that match the way that it expects, it can automatically process them. And when it gets receipts that it doesn't know how to, it can't recognize, it then sends those off to the dudes in a box who then type out the receipts. And if they get enough of the same look, they can get the computer programmer to add more looks. And so this is kind of mirrors the axiom theorem idea from before. If you need a new, if you need to detect a new layout, well, you can add in some axioms to your system to help it recognize when it's having these different types of receipts. And so eventually, once you identify a sufficient number of receipt layouts, most of your receipts can be processed automatically, and only a handful of them have to go to the dudes in a box. And so that's kind of how these AI systems kind of grow, is that you just simply whichever ones are the most prominent, those are the ones that you send to your programmer. Your programmer figures out how to process them, and then they go back in the system. And so this sort of using dudes in a box to manage artificial intelligence, it actually happens so often that Amazon Web Services has a special service that they sell to allow AI startups to do this. And so most people don't recognize Amazon doesn't actually make most of their money selling books or movies or anything like that. They make most of their money. Their biggest profit margin is actually selling computer infrastructure. So you can rent servers from them. You can have them do computation tasks for you. So that's actually their big margin product. And so they actually have a special service in this that they sell to allow AI startups to use dudes in a box, and they call it the Mechanical Turk. And so you can actually go and you can schedule jobs on the Turk. So like let's say you wanted to categorize your pictures according to how beautiful they are. Well, that's not something that computers are very good at recognizing. So instead, you can simply you could create a job in the Mechanical Turk to say, hey, will you categorize, how beautiful these photos are? And so you can basically write a program that calls out to a human and gets a response back. So you yourself could have an AI startup that uses dudes in a box. So in summary, humans and computers are different and are good at different things. Humans are better at axioms and judgments. Computers are better at building theorems from axioms. All right, and so these differences stem from the fundamental spiritual nature of humans. We're able to recognize self-evident truths, and computers can only do what they're told. So knowing more precisely the role of humans in machine learning allows you to better design processes and better to know how to split them between humans and computers. And in fact, oftentimes artificial intelligence systems wind up just being dudes in a box. And that's actually an effective technological solution that shouldn't be overlooked because humans are special. So by recognizing the fundamental spiritual nature of humans, we can actually lend ourselves to making better technological decisions when building artificial intelligences. So anyway, I hope you enjoyed this series. Again, the goal of these sketches, I don't expect you all to go out and make a artificial intelligence yourself tomorrow based on these principles. You might, if you're a machine learning specialist, that might be helpful to you. But my bigger goal is to help you recognize the fact that theology has practical value in whatever you do, and to open your mind to be looking at how does theology affect what I do every day. So anyway, I'll leave you with that. I hope you take it forward into your own life.